Octave equivalence is one of the oldest and most common relationships in music theory, dating back to Pythagoras. An octave is a distance between two notes, the higher of which has a frequency twice that of the lower note. For example, given a note with a frequency of 440, an octave above that would be the note whose frequency is 880. In O space, any notes that are one octave apart will be equated. On a keyboard, we designate octaves with middle C starting the fourth octave. But if we remove these octave labels, we can equate all the notes with the same letter name. Mathematically, this is known as modular arithmetic. Modular arithmetic is a system of mathematics which maps points onto a line of predetermined length. The integers of our coordinate system correspond to the 12-note chromatic scale. Therefore, we will be equating notes whose difference is plus or minus 12. Given a number greater than 12, but less than 24, we will subtract 12. Given a number greater than 24 and less than 36, we will subtract 24, and so on. It is important to note that in mod 12, the actual number 12 does not exist, but we can get infinitely close to it. Although we will be referring to the number 12 in O space, in reality by 12 we mean as close to 12 as we can get without actually equaling 12, known in mathematics as a limit. When we model this on a number line, it looks as if the points jump back to the beginning. Rather than having points jump, we can create a continuous space by folding a line through the second dimension and connecting the ends. We are all extremely familiar with another system that is mod 12, namely a 12-hour clock, in which half of a day is divided into 12 hours. If it is 10 o'clock and 7 hours pass, a 12-hour clock will show 5 o'clock rather than 17 o'clock, because upon passing 12:59, it returns to 1 o'clock. In our system, this will result in all of the elements of the space being greater than or equal to 0 and less than 12. When modeling a modular space, such as a clock which has only one dimension, we wrapped the ends around so that we could maintain continuous motion across the space and not have to jump from one end back to the other. For a one-dimensional space, we are forced to fold through the second dimension, creating a circle. Given a two-dimensional space, which contains sets with exactly two elements, we must fold through the third dimension in both directions, allowing for both the x-coordinate and the y-coordinate to maintain continuous motion. However, if we attempt to create a model in the next higher dimension, we would run into a problem. In order to model a three-dimensional space, we must fold through the fourth dimension, time, which is not possible as it is not a spatial dimension like the first three. This is the reason that we will be limiting our discussions of spaces to two dimensions. The analytic implications of octave equivalence, as with all equivalence relationships, is a loss of specificity. We are no longer able to distinguish between middle C and the highest C on the keyboard, or any other octaves. We are also no longer able to determine which note in a pair of Cs was higher than the other. While this might seem like a detrimental loss to analysis, octave equivalence still remains one of the most common equivalencies. The benefits of octave equivalence are so great that nearly every method of analysis requires it in some way. On the surface level, octave equivalence allows us to equate different voicings of the same chord, as well as octave shifts in melodies. However, on a more fundamental level, it is actually the basis of tonality. Octave equivalence allows tonal functions to be applied to the diatonic set of pitch classes. Without this equivalence, analysis would be severely restricted in the types of relationships they would be able to highlight.